The next thing we're going to talk about is really focusing on timbre. We mentioned that's one of the 6 main attributes that the brain can differentiate between various colors of sound. So what exactly is timbre, and what is our brain doing when it's processing timbre? Timbre is the combination of multiple frequencies happening in the brain simultaneously, as we mentioned before. So what I want to do now is to examine why that's happening, why does sound produce those multiple vibrations, and how does our brain process them at the same time. So in order to understand timbre, we have to understand what is the overtone series. Some people call this the harmonic series, it's sometimes the partial series. The overtone series is what happens when you have a vibration. Let's say we take a cello, for example. When a cello, we vibrate the cello, we set the string in motion, it sets the number of vibrations. The whole instrument resonates when a cello plays. We hear the sound, the pitch of the instrument, we can identify that, but we also can tell that it's a cello sound. And what's going on is the cello, because of the kind of wood that it's made of, the glue, exactly how much glue is built and used in making the instrument, all of those factors will affect how many other vibrations are happening simultaneously, or what is called the overtone series. The overtone series is the simultaneous sounding of a particular fundamental frequency, that's the pitch that we hear, plus divisions of that in various ratios. So for example, if we have a frequency that's 20 times per second, which would be a very low frequency, if we hear that sound 20 times per second, let's say that's a low pitch on the frequency. We hear the sound of the cello, we don't realize, but we're also hearing 2 times that. We're hearing 40 hertz or 40 vibrations per second, 3 times that, 60, 4, 5, 6, all the way up. Those vibrations are happening in our ear all the way up to whatever our ear can hear, which is 20,000 times per second. So everything in our ear is processing sound frequencies all the way up to 20,000 hertz. Collectively, we hear that as the timbre of a cello. If we were to hear say a bassoon or some instrument which has an entirely different timbre, we would be hearing a lot of the same frequencies, the same overtone series perhaps, but each of those vibrations would be louder or softer than the ones in the cello. So collectively, it's this combination of unlimited number of sounds up to our maximum hearing range, but then changing the amplitude or the volume of each one will change the timbre. So let's take a look at that for example. Here is a program which we'll be learning. It's called Sonic Visualizer, which enables us to look at sound. For example, let me get rid of these for a second and show you. If I just play the sound, this is a voice, obviously, and this is what we normally see as the representation of sound. We can start to see the vibrations. The height of these is the amplitude of the compression and the rarefaction. So as we were talking about on the oscilloscope, this is showing us an example of sound moving through time. And when we look at a lot of programs, we're seeing this conversion and representation of sound. On this program, I can also open up what is called a spectrogram, which now we start to see sound. If we look at this, this is the height of this is going to be the frequencies. So if there are colors going up, we will be able to see there's actually resonance or vibrations happening all the way up to 20,000. Actually, this goes up to 22,000 hertz. So some of us can't hear these sounds at the very top. The fundamental that we'll be hearing of that voice, we start to see a darker color, or in this case, a lighter color on the bottom. So the lighter the color means there's more volume. So when we're hearing the voice, we're actually hearing these very low frequencies down here. I could change this scale for a second so we can actually see a closer representation. Right now it's set up from 43 to 22,000 vibrations per second. If I change this and narrow it down to maybe 8,000 cycles, we can now start to see where these particular frequencies are down here and how strong they are. So we start to see now, this is the overtone series or the spectrum of that particular voice. We can identify which of these partials are vibrating, which ones are not in the sound, and which ones are strongest down here. I can also open up another pane and start to see where are the frequencies that have the peak frequency energy in them. And then you start to see which of the particular range, and I can identify over here which of the frequencies are sounding the most. So this would be our fundamental. And we start to see some very strong overtones are resonating at other parts. This might be called the first overtone is here. So what we're going to be doing in this class is trying to break down timbre. But in order to understand that, we have to understand the overtone series. So let's take a look at the overtone series. If I think about the overtone series, that might be the cello playing the low C, for example. So we would see the cello string vibrating. So the string would vibrate back and forth as the bow moves it. So the string is vibrating back and forth. If we put that on a time scale, then we would start to see it looking something like that. It's moving back and forth over time. And then as we listen to identify the overtones in the spectrum of the sound, we might discover the first overtone, which would be an octave above. If you don't read music, don't worry about this. We'll describe it without that. This is just a representation. So the very first overtone we would discover is exactly half the size, half the length of the fundamental, which that's the pitch we're hearing. So we could then draw two of those. So the fundamental is the longest one. Then a 2-to-1 ratio produces the first overtone, or the second overtone, which would be, in our mind, an octave higher. So that's those sounds plus 3-to-1 gives us the G. This would be, let's make this up for a moment. Let's say that would be 20 vibrations per second, or 20 hertz, we used to describe that. The next one is going to be 40, or 2 times this. The next one would be 60, or 3 times 20. We can go all the way up, identifying the pitches that emerge in the overtone series by just multiplying 4 times this, 5 times, 6 times. So if we figure out what frequencies are there, we can go right up the overtone series. Pretty much all of these overtones are sounding, and I'm just going to stop here. As you notice, the intervals between the overtones get closer together as we go up, because the ratios get closer as we go up. So the overtone series, all of these vibrations are vibrating simultaneously when we hear the cello because of the nature of the instrument, of the wood. So if let me erase this for a second. If I put the cello on a look at each one individually and put it on another kind of graph here. So let's say the fundamental is here. Let's say it's very loud. We measure amplitude in decibels. So let's say this is 100 decibels, which would be a very loud fundamental. So if I listen to the sound of the cello, for example, the fundamental frequency might be at 100 decibels. The second partial, let's say, might be something much less, might be at 28. I'm just making this up. The second partial. So this 40 hertz signal might be at 28. Maybe the third one, we would find it's a little bit louder, maybe at 30 hertz, 30 dB, excuse me. And the fourth one, each of these would have a different kind of spectrum to it. So that if I then connect all of these, we start to see that is the particular timbre or the spectrum of a cello. That represents that cello. If we ask, why does someone pay several $1 million for a Stradivarius cello, a cello built in Italy several hundred years ago, there is a particular quality to that cello. The timbre of that cello is very different than if we buy a modern mass-produced cello for $100. They both produce the same pitches, but what is the difference? It's the timbre. The Stradivarius cello may have, for example, if you analyze its sound, it may have louder amplitude on some of the low frequencies in the sound, which gives it, in our perception, a warmer, darker sound. So we prefer that sound, and we're willing to pay a lot more money to get an instrument which has those overtones that are louder. If you analyze the inexpensive, mass-manufactured modern cello, you may find that many of the higher overtones are louder in the spectrum. And what that does, it produces a brighter sound. So we may say, well, that's kind of tinny sounding, or doesn't sound quite as warm and deep. So what we're perceiving in timbre is the combination of understanding all of these overtones sounding simultaneously. We don't hear them individually. We only hear the fundamental primarily. But all of those other frequencies are in the sound in our brains, and that's what our brains make a connection between all of those, and we hear that as timbre. So timbre is the most important quality as we shift from designing sound and making sure that the timbre has a certain quality, because we perceive and people tend to respond to timbre in very, very quick aesthetic responses. So when we hear a sound very quickly, we can identify that as a pleasant or an unpleasant sound based upon its timbre. So in some ways, that's the most important of the attributes in understanding why people like or don't like sound, is understanding its timbre. We can now get into, which we'll do in this course, which is called synthesis. Synthesis is a system where we can build up various timbres. So we'll be learning to synthesize sound and break sound down into its individual overtones, and then start to create and adjust those overtones through filtering, all sorts of other processes, so we can adjust the timbre and change sounds from one sound to another sound just by changing its spectrum. But once you get to its overtone series level, then we have the ability to make those changes.
The preceding program is copyrighted by Emory University.